Dear student, warm welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. This lecture number 32. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. Name of the course Geosynthetics Engineering in Theory and Practice. This is Module 6, Lecture 32, Geosynthetics for Reinforced Soil Retaining Wall. This recap of previous lecture, we give example of horizontal stress on the retaining wall due to the wheel load, and also we showed the relationship between the horizontal stress with the depth. Now, Excel program for mechanically stabilized reinforced soil retaining wall we partly completed. Now, I will tell you about check for the adherency of the reinforcement. Check for adherence for reinforcement. Here, record factor of safety is 1.3 as per BS 8006 1995, and this is the ZJ for different depth, and this is the L, length of the reinforcement, that is 6.9 meter, is same all along the depth, and this is the L of G, embedment length, this 6.80, 6.48, and then continue up to the ZJ is 8 meter, 2.74. This embedment length value is more on the top, and then gradually it is decreasing. It is like a failure surface, then what should be the length of the embedment length. Then you know that L of nu will be equal to 6.9, the same as L we are keeping, and then L is a nu which is 6.80, 6.48, 6.17, 5.86, 5.55, 5.24, 4.92, 4.61, 4.30, 3.99, 3.67, 3.36, and 3.05 and 2.74, and ions here is 0. So, here for load case A and this B. So, here load case A, what is the TRJ? So, you can calculate TRJ 2135.56, and this is the safety factor for load case A. You can see this is 39.16, and then gradually this factor, partial safety factor, is decreasing, and it is about 9.31. So, it satisfies the criteria as per BS code specification. So, it is safe for load case A. For load case B, you can also calculate the TRJ. So, this is the TRJ value, and then you can calculate the partial safety factor, that is from 36.67 and is gradually decreasing to 30.83, and which is as per code it is 1.3. So, it satisfies this criteria. So, it is also the safe. So, due to pull out, the adhesive reinforcement is satisfying this criteria. Now, seismic analysis for external stability. So for external stability seismic loading as per FHWA NH1 00043. So it's a design of horizontal seismic coefficient AH as per IS 1893 2002. We are taking AH value is 0.18 and maximum wall acceleration coefficient for external stability, that is AM external, is 0.18. Maximum wall acceleration coefficient for internal stability, that is AM internal, is 0.18, and vertical seismic coefficient AB is minus 0.09. Now required factor of safety for seismic loading, this is come about 75% of the static value. Equivalent height of the retaining field H2 is 9.886 meter, and equivalent height of reinforced field H1 is 9.886 meter. Dynamic earth pressure coefficient KAE is 0.381 and dynamic earth pressure coefficient increment, that is delta of K dynamic is equal to 0.11. Now horizontal component of dynamic earth pressure, that is delta RH dynamic is equal to 117.1819 kilonewton. Calculation of interior force per meter run due to the mass of facing block, that is FH1R, FP is 8.076083 due to the mass of the crash barrier. I have told about the crash barrier in the beginning. So this is FH1RCB is equal to 2.943 due to the field and surcharge load, that is FH1RSQ is equal to 191.7521 and total is Z inertia force, that is delta RHLR is equal to 202.7712. Now horizontal force from static loading per meter run due to the soil pressure 189.2196, due to the dead load surcharge 69.29297, and due to horizontal steep load is considered 0. Total horizontal static force, that is RH static, is 258.5126. So total resultant force horizontal RH is 519.8747 kilonewton. Total horizontal force per meter run due to the weight of the field, that is 1153.128 kilonewton, due to the surcharge load 211.14 kilonewton, and due to the vertical steep load which is given 15 kilonewton, and due to incline of soil pressure it is 0. So total resultant vertical force RB is equal to 1379.268 kilonewton. Check for the sliding along the base and assuming factor of safety minimum 1.125. Force resisting the sliding along the base 796.8327. Factor of safety against the sliding available 1.530816. So minimum factor of safety against the sliding require 1.125. So therefore check for the safety against the sliding along the base. So we find safety along the base is safe. Now disturbing moment MD is 2174.714 kilonewton meter and resisting moment 4720.225. So check for the bearing capacity required, that is minimum 1.875. Eccentricity E is 1.604448 meter and effective width of the foundation is 3.691104. Then factor of bearing pressure is 373.6736 kilonewton per meter square. We know that bearing capacity factor, that is NC is equal to 30.14, N gamma 22.4, NQ 18.4, and water table correction factor RW is equal to 1, and ultimate bearing capacity, that is Q ultimate 994.6866 kilonewton per meter square. So minimum factor of safety required is 2.768605. So check for the safety. So check it is the safe. Check for the eccentricity. Eccentricity E is equal to 1.604448 meter. So allowable eccentricity E allowable 2.3 meter. Check for the eccentricity also is the same. So you check that eccentricity and you find it is the same. Now we will discuss seismic analysis for internal stability. Seismic analysis for the internal stability. So internal stability for seismic loading, required factor of safety minimum for internal sliding is 1.125. So this is layer 1, 2, 3, 4 up to 14 layer, and ZI is 0.2 meter to 8 meter. So this is the length of the reinforcement 6.9, it is constant throughout the depth, and HJ 8.16 to 0.36. RH HJ is kilonewton 498.78, and then it is gradually decreasing to 15.72 kilonewton, and RVJ is kilonewton 1457 for 57 to it is to 284.29. Then you check that what will be the partial safety factor. It is 1.39 and 1.48, 1.79, and this you calculated that partial safety factor, you know what will be the TD design divided by what is the TJ, that what is required. So you can calculate this factor of safety. So you can see that with the satisfying the criteria as per the BS code specification. So that's why it is the safe. So all these factor of safety is the safe. Now the seismic analysis check for the rupture. So here check for the rupture of the reinforcement and is required factor of safety 1.25. This internal inertia force due to the weight of the infill within the active waves is 107.8366 kilonewton. So this is the ZI up to 8 meter. This is HJ 8.16, the same 3.6. This is SVJ, that is the spacing 0.50, and then 0.6 is constant, and this is 0.66. Then what will be the MDJ? This 766.18, and then gradually decreasing to depth of 0.77. Then eccentricity 0.54. Then it is almost, it is 0 here, and this is the DJ. I explained all the earlier. This is 6.88 to 1.96, and this is TPJ, that is 28.62 is decreasing up to 7.32, and then this is the TSI, this kilonewton 0.36, 0.44, and then it is up to 1.35 at deep depth, and this is the TFJ, which is the 0, and this is the what is that T required, that is 8.36, and then going down to 3. This is 3.38. This is 3.38, and then TSJ also it is the 0. TJ is 37.35, and then it is decreasing up to 12.05. T of DJ 70.99, and then it is decreasing up to 28.40, and this is what is safety factor, partial safety factor. This is 1.90, 1.75, you can see 1.61, 1.4 and 2.65. So you can see that it satisfies this criteria as per the BS code specification. So it is safe. So we find that due to the rupture of the reinforcement, that our required factor is 1.25, and it is satisfying this factor of safety. So due to the rupture of the reinforcement, this design is safe. Now we will go seismic analysis, check for adherence of the reinforcement. Check for the adherence of reinforcement, required factor of safety 1.125. This is ZJ, this 0.228. This you know length is 6.9 constant, and this is LEJ 6.80 to 2.74. Then again TRJ kilonewton is 1366.19 and decreasing to 107.36, and then this is the partial safety factor 36.58, and it is decreasing to 8.91. So your requirement is 1.125. So it is the safe. So it is safe. So check for the adherence of reinforcement is also safe. Now here I will show that final reinforcement layout. Wall height is 8.9 meter, design height is 8.36 meter, and this is the layer. This is 1 to 14 layer, and this is ZJ is 0.2, 0.6 like this. This is I can say the 0.6 meter spacing or vertical spacing between the two reinforcement, almost 0.66 in this zone. Then length of the reinforcement is constant throughout, that is 6.9 meter, and T ultimate is kilonewton 150, then 120, then 100, then 80, and then 60. And TD is kilonewton per meter is 70.99, then again 56.8, 47.33, 37.87, and 28.4. So you can see that what should be the layout of this, that final reinforcement layout, what should be the spacing, and what should be the length of the reinforcement. Now we check for the connection strength. This is very important. Sometimes due to the connection, the reinforcement soil structure fail. So reinforcement load at the connection, height of the facing is 8.36 meter. This is the 1 to 14 layer. This is ZJ is 0.22. This is 8, and this is A0 is 0.994 to 0.761. TJ 64.64 to 17.99. So this is the maximum tension in the reinforcement, that is in static that is TJWS, that is 32.36, is decreasing up to 5.24, but when it is the seismic case, it is lesser than the static case, that is 27.23 to 4.22. Then serviceability, what is required, 27.412 to 2.704. That is the serviceability. Now, load at connection. This is talk about maximum tension in the reinforcement, either in the static and seismic, and what is serviceability. Now, load at the connection, the static TW is 32.16 to 4.03, and in the seismic it is 27.1 to 3.17, and serviceability requirement 27.25 to 2.08. So, we check this, what should be the reinforcement load connection, and we find it is on the safer side. And now almost we complete the design, but the here also this is check for the internal sliding. The required factor of safety 1.3 as per BS 8006 1995. The reinforcement layout detail here, this is 1 to 14 and Z value 0.2 to 8. This LL is 6.9 is constant, HJ is 8.16 to 0.36, and RH kilonewton 444.15 to decreasing up to 8.22, and RV is kilonewton 2 to 641.43 for the load case A, and this is the partial safety factor. This is 3.02 and increasing up to 46.42. So, your requirement is 1.2, so it satisfies the criteria. So, it is on the safer side. Now, this is for load case B, and this RHJ is 4.15 to 8.22, and RBJ is kilonewton 135.2.22 to 275.82, and then you calculate what will be the PSF, partial safety factor 1.81 to 19.92. So, this also safe because it satisfies the criteria as per the BS code specification. So, we almost complete this design for the reinforced soil, this retaining wall. So, there are numerous computer program is available from the manufacturer for their specific product, and also this is a kind of generic program that are commercially available, and it can be observed that GeoGit manufacturer have developed the different types of the design chart algorithm and also the graph for the specific product. It is very good, and you should consider this as a guideline. But you have to remember that design should not be based on the product, but design should be site specific. So, you should know what will be the site, and based on that you should design, because every time that there will be the change of the design, because for various factors that initially when the seismic force also are not taken into consideration, also sometimes the connecting strength also not been taken into consideration. So, always you should update this program and you should adopt the design which should be the latest design program. So design should be based on the site specific. So here some also GeoGrid reinforced earth wall, and this is wall is panel has been used, and this the first time in India about 15-meter height GeoGrid reinforced soil wall, and here this local fly ash has been used. This is the one first that GeoGrid reinforced soil retaining wall where the huge amount of the fly ash has been used. This is another segmented precast concrete panel reinforced soil wall. This GeoGrid reinforced earth wall in Ghansali in Navi Mumbai. Courtesy to Dr. Asa. This is modular block, concrete block. You can see that facing element is the different type, and this is complement to the Larsen and Toubro Limited. This is also GeoGrid material has been used. Here modular block wall in Kanjurmarg, and this photograph courtesy to Dr. Asa. Here GeoGrid reinforced soil panel wall in the Jaipur, it has been used. You can see different types of the panel. Here that you can see that how the railway train can pass through the GeoGrid reinforced soil wall. This is after Professor Fumio Shioka, Japan. And so you can have some the idea about this. Now I will address part 2, geotextile or the GeoGrid wrap around face mechanically stabilized earth wall. So this is will cover general and design of geotextile wrap around face wall, internal stability, external stability, and wrap around face construction detail. So this is the kind of the woven geotextile material, and we will use in the design this kind of the woven geotextile material. It can be wrap. So this is wrap facing, wrap. This is the wrap facing. We can also use the non-woven geotextile material. It's like this, and it can be also wrap. So we will design this geosynthetics material, either it is a woven or non-woven. Even then, we can also use the GeoGrid material as a wrap as a facing. So wrap around facing wall is less expensive than any concrete facing block or panel. Now this design is based on certain assumption, that is the classical ranking earth pressure distribution is used. The geosynthetics extend beyond an assumed ranking failure surface or plane. As the design is conservative, ranking active earth pressure coefficient Ka is used. The classical Coulomb active earth pressure coefficient is less conservative. Bouguereau's elastic theory is used for the live load. So here I am showing that geosynthetics wrap around face reinforced soil wall. So here is the foundation, and this foundation soil has a property of pi f and the gamma f. This is angle of internal friction of the foundation soil, and gamma f is the unit weight of the foundation soil. This is the geogrid material and this is the wrapping like this, and you fill up with the soil, and then the next layer of the woven or non-woven geotextile material, and then it is wrapping. Like this you can construct a reinforced soil wall with height is equal to h. And it also has a retained backfill soil, which unit weight of the backfill is expressed as gamma b and angle of internal friction of the backfill soil pi b. And also here is the reinforced zone, where unit weight of the reinforced soil gamma r and angle of friction of the reinforced soil is equal to pi of r. So this is the active zone and this is the passive zone. There is also the surcharge load here on the top of the wall, and apart from that there is a live load. Here is the live load, and this is the ranking failure line, which divided this reinforcement into two zones. This zone we call active zone and this zone we call the passive zone, and you can see how the friction develop between the soil and the reinforcement, and shear stress is mobilized along this direction and also along the facing element. And this distance, what you call L of E, it is called the embedment length or the bond length or adherence length, and this is the LR, this is non-active length in the active zone LR. So this is total length is L, so L will be equal to LE plus L of R, and this is height of the wall H, and this failure plane making at an angle of 45 degree plus pi by 2, and this length is equal to L of 0, L of 0, and spacing between the two geotextile material is designated as S of B. So you can calculate at any depth Z what should be the length, embedment length L of E or L of R, or what should be the total length. So geocentric wrap around face reinforced soil wall. Now for this part I say that you require physical properties of wall, that is height of the geotextile wall, length of the geotextile. You require properties of the reinforced soil zone and backfill soil zone. I show you gamma unit weight of the backfill or the reinforced soil. If it is a backfill, gamma b; if it is a reinforced soil, then gamma r. Pi friction angle of the backfill or reinforced soil. I show if it is a backfill is pi b, and if it is a reinforced soil zone, it is a pi r. And C is cohesion, or CA you can say adhesion. Properties of the foundation soil: gamma f unit weight of the foundation soil, pi f friction angle of foundation soil, and CR is cohesion of the foundation soil. And the loading Q is the uniform surcharge loading, and P is the live load, which we have seen also in the figure earlier. Now this is the locus of the maximum tensile force line. It is assumed like this. You can see maximum tension here, either it is a woven or non-woven geotextile material. This is that ranking failure surface just shown. It has also earlier it has been shown. So now in this wall, what are the earth pressure distribution along the geocentrics wrapped around face reinforced soil wall? So we need for the internal and the external stability of the wall, and that you should check properly. You can see here that if this is the wall and this is the assume that ranking failure plane, and this is the surcharge height is small h, and there is also live load. and the earth pressure distribution along the geosynthetic wrap around face reinforced soil wall. What will be the earth pressure is acting on the wall. This the triangular distribution due to the soil pressure. So, this is due to the soil pressure. This plus due to the surcharge pressure. So, this is the surcharge pressure plus there is a live load. So, this is the live load pressure. So, all this pressure you have to take into consideration for the design. So, pressure due to the soil, pressure due to the surcharge as well as pressure due to the live load. So, this will give you what will be the total pressure. So, total pressure will be equal to the soil pressure plus surcharge pressure plus live load pressure. So, first of all you have to calculate that what are the pressure are acting on the back of the reinforced soil retaining wall. So, when we design is go for design for the internal stability as well as external stability. For the internal stability you need ultimate limit state. That means this geotextile material may fail due to the tension, pull out or anchor failure, and factor of safety should be greater than equal to 1.5. Also you have to check the serviceability limit state. That means wall face deformation, how much is to deform. So, that part you have to consider as a internal stability. This is all ultimate limit state. For external stability, what is the ultimate limit state? This geotextile reinforced soil wall failed due to the sliding at the base. Anti-recoil factor of safety should be greater than equal to 1.5, or the geotextile reinforced soil wall failed due to the overturning, and you have to check what will be the factor of safety against the overturning, and that should be greater than equal to 2.0. And also it may fail due to tilting or bearing capacity of the foundation soil. So, the factor of safety should be greater than equal to 2.5, and global slip or deep seated stability failure, that means factor of safety should be greater than equal to 1.3. So, seismic stability you have to check, and check the factor of safety should be greater than equal to 1.1, and also you have to check serviceability limit state, that means what should be the settlement. So, you have to check serviceability limit state for the wall face deformation and also serviceability limit state for the settlement. Now, when you construct this wall and how you can construct this wall. So, this is wrap around face construction detail after Stewart and Moyni in 1982. So, what you have to do that you have to, for example, this is the ground surface and you want to construct a wrap around face retaining wall. So, you have to remove first of all that all unsuitable material from the site and compact in situ to achieve the desired foundation soil. So, no concrete foundation is needed for this structure. And then you place the geotextile. This is dot dot, this is the geotextile material. Place the geotextile and unroll it. You can have it in the roll form, you can unroll it over the selected this foundation and using a, this is the temporary wooden fence form. This is the wooden frame form. This is the false one, and it is a L shape wooden form placed along the length of the wall, and geotextile of around 1 meter hang, 1 meter hang behind this form. So, this is first stage, and then you have to fill up with the soil and compact it to the desired height. Now you are placing this backfill material, and this up to about 200 millimeter to 400 millimeter, and compact it with a lightweight hand operated vibratory compactor. But you have to maintain this depth of the backfill material within 200 to 400 millimeter, in order that this geotextile material may not be damaged during the compaction. So you should maintain this height. Now next is you are to this next, the geosynthetics is folded back over the backfill material. So minimum return length should be 1 meter. So this to this, it should be minimum, this should be minimum, that is what we call the overlap length, and which is called the L of 0. This should be minimum 1 meter in order to satisfy the stability of adequate pull out resistance. Now this wooden face form now is to be removed. You have to remove this. This wooden frame form is to be removed from the front wall, and then this is to be placed over the compacted layer. So you have to remove it and place in the compacted layer like this. You can place of the compacted layer. So this is initially, previously it was here. This is the previous lift geotextile strip. This is the wall face. Okay. Then this is the wedge to level, and then wooden face is removed from here, and then you have to place over this compacted layer. The same procedure, you place the geotextile again, and geotextile will hang up to 1 meter. This is nothing but a false that wooden block, and the same procedure continue until it reaches the desired height of the wall. So like that you can construct this wall. In general, if the height of the wall is more than 2 meter, it is necessary to provide the scaffolding. You can provide a kind of the scaffolding in front of the wall. Or wraparound facing cannot be kept the open. You cannot keep this that geotextile wall in the open to the sunlight due to UV radiation. Therefore, it should be covered by spraying the bitumen emulsion, concrete mortar, or shot kit of thickness about 150 millimeter to 250 millimeter. Suppose in case of the geogrid, so in case of the geogrid, so you can provide a geotextile material here is needed to retain the backfill material in front of the face wall. So this is the geogrid material, and then you are wrapping like this, and you can provide with this is a gravel which will also act as a drainage, and then you place the geotextile material and can wrap it, because this is the reinforcement fill. So this reinforcement fill material should not come out from the geogrid material, or this reinforcement fill material will act also as a separation and also as a good drainage material. Also the grass can grow on the back of the wall. Now design of a geotextile wrap around soil retaining wall of 5 meter height. This is one example, and we are giving that soil properties of the reinforcing zone, that is unit weight of reinforced soil gamma R is 17 kilonewton per meter cube. Cohesion of reinforced soil CR is 0 kilonewton per square meter. Angle of internal friction of reinforced soil pi r is 35 degree. Angle of friction between soil and reinforcement delta is 25 degree. Ultimate tensile strength of geotextile T ultimate 60 kilonewton per meter, and factor of safety is equal to 1.6. Now properties of the existing backfill. Unit weight of the existing backfill gamma B is 17 kilonewton per cubic meter. Cohesion of existing backfill Cb is equal to 0. Angle of internal friction pi b is equal to delta is equal to 35 degree. Properties of foundation soil. Unit weight of foundation soil, that is gamma F is equal to 18 kilonewton per cubic meter. Then cohesion of foundation soil Cr 22 kilonewton per meter square. Adhesion between soil and the reinforcement Ca is 0.8 into Cr. You know what is the Cr, and then you can calculate Ca is about 17.6 kilopascal. Angle of internal friction pi r is equal to 15 degree. Angle of friction between soil and reinforcement delta r is 0.95 of pi f, that is 14.25 degree. So this is the wrap retaining wall, which properties is given. This height of the wall is 5 meter, and this is the surcharge load, and here is gamma r pi r is given. Here is gamma b pi b is given. Here is the foundation Cf delta and Ca is given. So you have to design this wall. Now the solution for the internal stability. Step 1, calculate the total horizontal stress behind the given retaining wall. This is the wall, and this is the soil pressure due to the backfill, that is designated at sigma of Hs. So horizontal earth pressure due to the backfill will be equal to Ka into gamma b into Z. At any depth you can calculate what will be the horizontal earth pressure due to backfill. This plus this horizontal earth pressure due to the surcharge load. Here there is a surcharge Q is 15 kilopascal. So surcharge is given. So you can calculate what is the sigma of Q. The horizontal earth pressure due to surcharge will be equal to Ka into Q. So you know Ka because you know pi b, so you can calculate Ka, and you know what will be the Q, so you can calculate the horizontal earth pressure due to surcharge. Now this total pressure will be equal to the horizontal earth pressure due to backfill, horizontal earth pressure due to surcharge. This is the total pressure. So this is total horizontal stress behind the reinforced wall. That means if it is a sigma Hs plus sigma Hq. So total horizontal stress behind the retaining wall is equal to sigma Hs plus sigma Q. Now at any depth Z below the wall top, you can calculate. That means you know sigma H is equal to sigma Hs plus sigma Q, and sigma Hs is equal to K gamma B into Z plus K into Q, where K coefficient of active earth pressure of backfill, gamma B unit weight of the existing backfill, that is 17 kilonewton per meter cube, and Q is equal to surcharge over the wall top, that is 15 kilopascal. So you can calculate the K using the equation K is equal to 1 minus sin pi b by 1 plus sin pi b, where pi b is equal to angle of internal friction of backfill soil, that is 35 degree. So K will be 1 minus sin 35 degree divided by 1 plus sin 35 degree is equal to 0.271. So if you calculate that sigma of H, so sigma H is equal to K value is known 0.271, gamma V value is known 17 kilonewton per meter cube. So, and Ka value also known, Q value also known. So, if you substitute this value Ka, gamma B and Ka and Q, so you can have the sigma H in terms of the Z. So, if we calculate sigma H will be equal to K 0.271 into gamma B is 17 into Z, that means it will give 4.61 Z, plus K is 0.271 into Q is 15, so it will give 4.065. So, you can calculate that sigma H is equal to this in terms of the Z. So, you have calculated. Now, step 2, you have to calculate the allowable tensile strength, that is T allowable. So, T allowable is equal to T of ultimate by reduction factor. Now, this is reduction factor which we call the cumulative reduction factor, that here we are considering that 4.68, and you are to select that all these factor, that is what will be the factor for the creep factor, reduction factor for the creep, reduction factor for the installation damage, and reduction factor for the chemical and the biological clogging. So, these are the reduction factor you can obtain from the reinforced soil retaining wall, and these all you call the cumulative reduction factor. So, we are considering the cumulative reduction factor RF is equal to 4.68. So, we know that T ultimate is equal to 60 kilonewton per meter given. So, T allowable will be equal to 60 by cumulative reduction factor 4.68. So, it will give 12.821. Step 3, you have to spacing of the reinforcement SB and the number of the layer. So, SB is the spacing will be equal to T allowable divided by sigma H into factor of safety, or SB is the spacing between the reinforcement layer, and factor of safety is equal to 1.6. So, T allowable will be equal to 12.821 kilonewton per meter, which we previously calculated, and we know also previously that sigma H is equal to 4.61 Z plus 4.065. So, therefore, this S of V, this SV will be equal to T allowable we calculated 12.821, this divided by this sigma H in terms of the Z, that means 4.61 Z plus 4.065 into this factor of safety, that factor of safety is 1.6. So, we can obtain the SB in terms of the Z. So, ultimately we will have that SB is equal to 12.821 divided by 4.61 Z plus 4.065 into 1.6. Now, you have to select the Z from the top. So, we are providing that 5 meter and spacing is 0.3 meter. So, when depth is Z is 5, and what is SB? So, you substitute the value of Z is equal to 5, because this is the height of the reinforcement is 5 meter. So, SB spacing between the reinforcement will be 0.3 meter. Now, you can consider middle somewhere. So, you have to assume some Z value, let us say Z value from the top is 3 meter. So, you substitute the Z value here 3 meter. So, you can calculate what will be the spacing. So, spacing will be equal to 0.45 when the Z value is 3 meter. Next, this 1.5 meter. So, at the 1.5 meter, you substitute this value, you can update SB 0.75. So, top 2 layer is taken as this 0.7 meter. That means 2 into 0.7 meter is equal to 1.4 meter. Now, provided spacing from the bottom and the number of layers. So, this is the layer from the bottom. So, if we can 6 layer from the bottom and spacing is 0.3, So what will be the remaining height? That means 5 is the height of the wall minus 6 into 0.3. So this is 3.2 meter. And then you are providing 4 meter, is 4.5 meter spacing. So this will be 3.2 remaining height, 3.2 minus 4 into 0.45. That means this equal to remaining height 1.4 meter. And then layer from the bottom 2 and spacing is 0.7. That means 2 into 0.7, 1.4. This is 1.4 minus 2 into 0.7. That means it is 0. So you can see here that total layer, how many total layer it will be. So here is the number of the layer of the reinforcement, that is that 12. Total number of the layer will be equal to the 12. So this is the 6 plus 4, 10 plus 2. So total layer will be the 12. So here to length of the reinforcement in step 6. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is top. Then you have to calculate what will be the length of the reinforcement. And here this is the LE, it is embankment length, and this is the LR. So this is the total L will be equal to LE plus L of R. So this is the H, and at any depth Z, this is H minus Z, and this is the failure plane, which is making at an angle of 45 degree minus pi by 2. So we know that LE is equal to SB into sigma H into factor of safety divided by 2 into gamma R Z tan delta R plus C of A. So SB will be equal to T allowable divided by sigma H into factor of the safety. So hence LE is equal to T allowable by twice gamma R Z tan delta R, because CA is equal to the 0. And T allowable we calculated, that is 12.821 kilonewton per meter, it is previously calculated. So gamma R is unit weight of the reinforced soil, that is 17 kilonewton per meter cube, delta R 25 degree, tan delta R is equal to tan 25 degree is equal to 0.4663. Therefore, LE will be equal to T allowable is given 12.821, and this 2 into gamma of R, gamma R is 17, this is 17, and this is the Z, and tan delta R is equal to 0.463, so 0.463. So this LE in terms of Z, this is 0.81 divided by Z. So LE is equal to 0.81 divided by Z. For various values of Z, so you can calculate what will be the L of E. So if you know the LE, you can calculate LR, that is length of the Z textile in front of the failure line up to the facing. LR is equal to H minus Z into tan 45 degree minus pi by 2. We have also earlier discussed about this. So H is equal to height of the retaining wall, and Z depth from the top, and pi angle of internal friction of the soil 35 degree given. So LR can be calculated. LR is equal to H is 5 meter height minus Z into tan 45 degree minus 35 by 2, that is equal to 2.60 minus 0.52 Z. So for any value of Z, so you can calculate L of R. So you can calculate total length is equal to LE plus LR. So from this equation you can calculate L of R, and for this equation you can calculate LE, because Z at any depth you can calculate. And this is LR. If this 45 degree plus pi by 2, this is 45 minus pi by 2. So this LR we have considered H minus Z tan 45 degree minus pi by 2. So this is what it is written here. Okay, at that depth, because at any depth, this is pi by Z. So LE can be considered. Now assume that L0 and overlap length generally provided 1/2 of the embedment length. Therefore, L0 is equal to half of LE, that is SB into sigma H into factor of safety divided by 4 gamma R Z into tan delta. So as you know, LE is equal to 0.81 by Z, which we previously calculated. So L0 will be the half of this LE. So 0.81 by Z by 2, that means 0.405 divided by Z. So if you know any Z, then you can calculate L0. So then you can calculate what will be the total length. That means L total will be the, what will be the total length, then what will be the spacing between the two geotextile material SB plus this is the L0. So it is like this when you calculate that in terms of the total length. So if this is the geotextile material and this is the spacing, and here is the spacing is equal to SB, here is the total length, that means LE plus L of R, and here this is spacing, and here is the overlap length, that is what you call L of 0. So total will be L plus SB plus L0. So that's why L of total is equal to L. L also is equal to LE plus L of R. So this is L plus this is SB plus this is L of 0. So you can calculate what will be the total length of the geotextile material. So I ended up this lecture today. If any question, thank you for listening.